In this video, we will learn how to use adiabatic processes to determine the temperature of a parcel of air as it is forced to rise up and over a 4,000 meter high mountain. The initial temperature of the parcel at sea level is 30 degrees Celsius, and the lifted condensation level of the parcel is 2,000 meters. The dry adiabatic lapse rate, abbreviated DAR, is 10 degrees Celsius for every 1,000 meters, and the saturated adiabatic lapse rate, abbreviated SAR, is 6 degrees Celsius for every 1,000 meters. Before we can begin determining these temperatures, we must first understand one concept. The lifted condensation level, abbreviated LCL, is the location in the atmosphere in which cloud formation can occur. Until this elevation is reached, no clouds can be formed. The reason this is important is because it dictates when the DAR and SAR values are used, as the DAR is used until the LCL, and the SAR is used once you are above it. Now that we understand the LCL, we can develop an equation for determining these temperatures. The equation is starting temperatures in degrees Celsius minus A times 10 degrees Celsius minus B times 6 degrees Celsius. So what values go into A and B? A is equal to the elevation you are currently at when below the LCL divided by 1,000 meters. B is equal to the elevation you are currently at when above the LCL divided by 1,000 meters. The critical item to remember here is that once you are above the LCL, you must subtract the elevation of the LCL from your current elevation and use the LCL elevation as the value of A, as you must account for the temperature decrease up to the LCL. This should make more sense as we continue through these examples. In example A, we know our current elevation is located at 1,000 meters. This elevation is lower than our 2,000 meter LCL. Using our equation from above, we can determine the value of A to be 1 and B to be 0. B is equal to 0 because we are below the LCL, and A is equal to 1 because 1,000 divided by 1,000 is 1. Putting these numbers into the equation, we are able to solve that the current temperature is 20 degrees Celsius. In example B, we know our current elevation is located at 3,000 meters. This elevation is higher than our 2,000 meter LCL. What this results in is a value of 2 being used for A due to the fact that we must account for the temperature decrease up to the LCL. Then subtracting the LCL value from the current elevation, we are left with a value of 1,000 meters, which is the distance we are above the LCL. Using our equation, we can determine the value of B is equal to 1, and then putting these numbers into the equation, we are able to solve that the current temperature is 4 degrees Celsius. In example C, we know our current elevation is located at 4,000 meters. This elevation is higher than our 2,000 meter LCL. What this results in is a value of 2 being used again for A because we must account for the temperature decrease up to the LCL. Then subtracting the LCL value from the current elevation, we are left with a value of 2,000 meters, which is the distance we are above the LCL. Using our equation, we can determine the value of B to be equal to 2, and then putting these numbers into the equation, we are able to solve that the current temperature is -2 degrees Celsius. Thus far, we have learned how to determine the temperature of a parcel of air as it rises up a mountain, but what happens when you begin to descend the mountain? What one must remember about the temperature as you are rising up a mountain is that temperature is decreasing due to the compression of the parcel. As one descends, the parcel of air expands, resulting in increasing temperatures. With this being known, we can determine the temperature of a parcel of air as it returns back to sea level. This, however, requires a new equation to be used, as a descending parcel of air uses the DAR as it descends and does not use the SAR at all. The equation is starting temperature in degrees Celsius plus A times 10 degrees Celsius. Just as before, A will be equivalent to the current elevation of the parcel divided by 1,000 meters. Please note that the starting temperature of the parcel is not the original starting temperature, but instead is the current temperature of the parcel from where you begin descending. In this final example, we know our current elevation is located at 4,000 meters, resulting in a value of 4 being used for A. Using our equation, we were able to solve that the final temperature of the parcel of air is 38 degrees Celsius, which, as expected, is higher than our starting temperature of the original parcel of air. In summary, in this video we have learned how to determine the temperature of a parcel of air as it rises from sea level, up and over a mountain, and ultimately ends back at sea level. The important items to remember from this video are that two lapse rates are used at very specific times and are reliant on where the lifted condensation level occurs. Please feel free to share your comments and questions with your instructor regarding the content of this video, as well as receive further guidance on the concepts covered.